Welcome to Question Bank. This is the third part of the solutions of OPSC Assistant Engineer Electrical Engineering 2012-13 exam, and this is the third part containing the questions from 100 to 150. That means the final part. Because one paper, this is paper 2 is purely electrical part, and I am solving this one. I have already uploaded 2 videos containing 50 questions each, and this one is the last part. And let's have the first question, that means 101 question. That means here this one is a 101 question. A resistor connected across the gate and cathode of an SCR in a circuit increases its. So here given that the resistor connected across gate and cathode, that means in parallel across gate and cathode. So if we see the protection circuit of a gate, so this is the protection circuit of gate. Here is one resistor and here is another resistor and capacitor and along with a Zener diode. So which element is used for which type of protection? So here capacitor and resistor both are used for bypassing the noise signal, and the Zener diode is used for the gate over voltage, because Zener diode maintains the voltage at a constant level. So this is used to protect the gate circuit from over voltage, and the series resistor this one is used for over current protection. So now in this question, this is given that the resistor connected across gate and cathode, that means it is asking about this one, gate and cathode. This is gate, this one is gate and this one is cathode, and this resistor is connected along with that capacitor for the reduction of noise or to bypass the noise signals. Noise signal will provide immunity against false turn on or false triggering. So this is the answer. C will be the correct answer, that is noise immunity. Next question is, which of the following will not cause permanent damage of an SCR? So you will find in maximum places the answer will be high current. There will be answer will be high current, but in my opinion this is not the answer. The answer is high rate of rise of voltage. Because the question is asking for which of the following will not cause permanent damage, because in case of high current it will increase junction temperature and it will damage the SCR. Next one is high rate of rise of current. If we explain this one, high rate of rise of when the thyristor is turned on by gate pulse, then a charge carrier spread through its junction rapidly. But if rate of rise of anode current, that is di by dt, is greater than that of spreading of charge carrier, then localized heat generation will occur, and this will take place at some places. This is called the local hotspots, and this will damage the thyristor. So both the cases, this is damaging the thyristor and this is also damaging the thyristor. And next one is high temperature rise, also causes permanent breakdown of the junction, because as the temperature rises, maximum number of charge carrier will be available and more current will be flow, and this will gradually damages that junction. So both A, B and C causes permanent damage to SCR, but high rate of rise of voltage will not cause the permanent damage. This will cause the false triggering or unwanted triggering or unwanted turning on of that SCR. This will cause false triggering. So in my opinion, this is the perfect answer for this question. So for next question is a SCR has an anode supply of sine voltage 200 volt RMS 50 Hz applied through a 100 ohm resistor and fired at an angle of 60 degree. Assuming no voltage drop, the RMS value of the output voltage is. This is simply an SCR has an anode supply of sine. This one is simply the single phase half wave rectifier, single phase controlled half wave rectifier, because SCR is used in case of instead of diode. If diode is used, there is no control term will be in the picture. So here SCR is used. So this is single phase controlled half wave rectifier. So this is the formula, you will directly find it in any book. So this is the direct formula if we apply this one, because this is given that Vm is equal to 200 into root 2. 200 is given RMS value. So this will be 200 into root 2 by 2 root 5, and this will be pi minus pi by 3. Pi by 3 is the 60 degree given here, 60 degree given here, and plus half into sine 120 degree. 120 degree means 2 into 60 degree. So it will be around 126.7 volt. So output will be 126.7 volt output RMS value. Next one is, when sine wave is given as input to Smith trigger, then it generates option A sine wave, option B sawtooth wave, option C triangle wave, option D square wave. So Smith trigger circuit is like this. Smith trigger circuit is like this, and this is a bistable multivibrator. And bistable operation of Smith trigger requires an amplifier with positive feedback. So always in case of Smith trigger circuit, positive feedback is given, and this is inverting amplifier. And if we see this one, this is the multivibrator output diagram, and if we see from this one is the input, this one is the input. From when input is greater than V upper threshold, this is VUT, this is upper threshold, and this one is the lower threshold, VLT, this is lower threshold. And when voltage is increased, and from increasing from upper threshold to lower threshold, that means from upper threshold to lower threshold, upper threshold is positive value and lower threshold is negative value, from upper to lower. So what is happening? From upper to lower. So this one, from upper to lower, mark the arrow mark, arrow mark is given like this. From upper threshold to lower threshold, what will be the value? Value will be negative saturation value. So what will be the value? Negative saturation value. So for this time, this will be negative saturation value. And when the sine wave is crossing the lower threshold value to upper threshold value, that means this one, lower threshold to upper threshold, like this. So what is it is taking from lower threshold to upper threshold in this way. What will be the value? Value will be the positive saturation. Value will be positive saturation, and this will be repeated. I am explaining only one cycle, and this will be again repeated. Again it will be negative saturation and it will be positive saturation. So simply this will come to be a square wave. This will be a square wave. So answer will be a square wave. Next question is 105 question number. The output clock frequency of a frequency division circuit having 11 flip-flops with an input clock frequency of 20.48 MHz is. So this is asking for the input clock frequency is given to be 20.48 megahertz and asking for the output clock frequency if in the circuit we have used 11 flip flops. So as 11 flip flops are used, this will divide the input frequency into 2 to the power 11 parts. 2 to the power 11 means 2048 parts. So what will be the output frequency? Input frequency by number of divisions. So this will be output frequency will be input frequency by number of divisions. So this will be our input frequency is given to be 20.4 into 48 into 10 to the power 6. That means 20.48 megahertz by 2048. That is the number of divisions, and this is coming to be 10 to the power 4 hertz. That is 10 kilohertz. 10 kilohertz. So answer will be 10 kilohertz. So next question is question number 106. On a master slave flip flop, master is enabled. Option A, when gate is low. Option B, when gate is high. Option C, when gate is either low either high. Option D, none of the above. So here nothing is given about the slave circuit or anything. So we will understand why this question is given like this. So what is the master slave flip flop? This is the master slave flip flop. In this thing we have to consider this one, this NOT gate, this NOT gate. So here if the master is enabled by signal 1, if the master is enabled by signal 1 or high signal, then slave will be enabled by the signal 0 or the low signal. This is the question. So if the question is given like this, if slave is here, suppose here given like that, if slave is turning or on or enabled with low signal, then what will be the signal for enabling the master? So here nothing is given. So we can tell that for a positive edge triggered flip flop, if master is a positive edge triggered flip flop, then what will happen? This will be on at 1, this will be on or enabled at 1, and the slave will be enabled at 0. And if the master flip flop is a negative edge triggered flip flop, that means when the triggering will be happen when this will be low, this will going to low, clock circuit will be low, this will be enabled. So if this is a negative edge triggered flip flop, then this will be enabled at 0 and slave will be enabled at 1. So as in the question nothing is given about which type of triggering flip flop this is, either positive triggered or negative triggered. Suppose this in this question this is given that this is a positive triggered flip flop, then this will be high, question answer will be high. If this is given to be negative edge triggered flip flop, then this will be low, question answer will be low. And if also the question given in terms of the slave enabling level of the slave, this is also we can determine. As this is nothing is given, either nothing is given about that triggering and the slave, we can say that when gate is either high or either low, if there should be mentioned positive edge triggered or negative edge triggered, this should be mentioned here in the question so that we can answer this one. So now next question is a JK flip flop with J is equal to 1 and K is equal to 1 has 20 kilohertz clock input. The Q output is option A constant and low, option B constant and high, a square wave with 20 kilohertz frequency, a square wave with 10 kilohertz frequency. So here given that JK flip flop, and we have to first point out the characteristic table of that JK flip flop and given that J is 1 and K is 1. So here this is the characteristic table of JK flip flop, and what is happening for 0 0 J is 0 and K is 0, no change. For Q T plus 1, that means this will be Q, that means the previous value. For J is equal to 0 and K is equal to 1, this will be 0. That means it is not depending upon the previous value, it is directly will be 0. And the for 1 and 0 this will be 1, and for 1 1 this is toggle, that means if Q is 0, Q T plus 1 will be 1. If Q T is 0, this will be Q T plus 1 will be 1, and if this is 1, then this will be 0. That will toggle will occur. So, and this is given that 20 kilohertz clock input. So here clock is given to be having the frequency of 20 kilohertz. So I have drawn this one is the wave, this one is the wave of a clock, and as this is a positive edge triggered flip flop, here as the positive edges, and only at this point triggering will occur, and as J and K are both are equal to 1, toggling will occur at the output. So suppose the output is 0 initially. Suppose the output is 0 initially. Here 0 initially. So what will happen when here is the clock is applied at positive edge? This will be 1, and this will be 1 till the next positive edge, and here is the next positive edge, and this will again toggle occurs means from 1 to 0, and this will wait till the next clock, and next clock is this one, and this will again toggle from 0 to 1. So output will flow like this. That means here the time period is doubling. So time period, here the clock has time period, suppose this one from this to this, and here from this to this, time period is doubling. That means time period is doubling means the frequency is halved. So this will be a square wave with 10 kilohertz frequency. If the clock has 20 kilohertz frequency, this will have 10 kilohertz frequency. So here answer will be option D. Next question number 108. For each of the positive edge triggered JK flip flop used in following figure, the propagation delay is del t and clock frequency is 1 by t. The output Q1 will be of a pattern. So I have already explained the JK flip flop here. What is, if frequency is, suppose here frequency is suppose given f is equal to 1 by t and delay is del t. So what will happen? Suppose this one is clock and these are the positive edge triggering labels. I have already explained in the previous question. So this is very simple now. So this will be like this. Already explained, and only here one term is extra. This is the propagation delay, and propagation delay will apply to the whole flip flop circuit. And this will be if this is going to be start from this will start from this. This is answer will be start from this. That means this delay is the propagation delay. That is del t. So now here propagation delay is already pointed out in the options. So options are here given. Here option are given. Suppose here 2t time period is given to be 2t, and here time period is given to be 4t, 2t, but delay is of 2t. This is not the answer. And here 2t is given. I have already explained why 2t. So here this one is one correct. 4t is not the answer. Next one is 4t. This is also not the answer. So propagation delay is t1 plus del t, and time period is 2t, and frequency will be halved. That means here frequency was 1 by t, and here frequency will be 1 by 2t, that means f by 2, frequency will be halved, So will the next question, question number 109, the logic function implemented in the given circuit is, here this one is a 4x1 mux, and as this one is 0, as initially this one is 0, here this one will be 1, and as this is connected like this one will be 0, this one will be 1, this one will be 1, and this one will be 0, and this is a NOT gate. And now we will write down directly the 4x1 mux formula, and this is the 4x1 mux output function, and this is S0 bar, that means 0 0 I0, S0 bar S1 bar I0, and S0 bar S1 I1 plus S0 S1 bar plus into I2, and like this. So now if I put the I0, I1, I2 and I3 values, this will be 0 because this one is 0, and this is 1 and this is 1, so this will be, here this will be 1 and this will be 1, and again this is 0. So here S0 is Q and S1 is P, so this will be Q bar P into 1, Q P bar into 1, and this will be Q bar P plus P Q bar, and this is simply the JOR gate. So function is JOR of P and Q. So answer is option D. Thermal runaway, next question is thermal runaway is not possible in FET, field effect transistor, because as the temperature of a field effect transistor increases, option A, mobility decreases, option B, the transconductance increases, option C, drain current increases, option D, the none of the above. So here if we check, first one is the answer, that is the mobility decreases, and option B is given that transconductance increases. Actually transconductance decreases as temperature increases, transconductance of FET decreases, and drain current decreases. Actually drain current remains stable, somewhat stable, and none of the above is not the answer. So here I am explaining, in case of BJT, that means bipolar junction transistor, in case of BJT, if temperature increases, what will happen? Base to collector junction temperature will increase, and that will cause the ICO, that is the reverse saturation current, that is the leakage current will increase, and that will again cause the collector current to increase, and as the collector current increases, power dissipation in terms of heat will increase, and that will again cause the temperature increase, and this is become a cycle, and at the result, after some time the BJT will be damaged. But in case of FET, as the temperature increases, it will depend upon the ID, that is the drain current. And one thing, when temperature increases, WD, that means the width, that is the deflection width. Suppose this one is the FET, this one is the FET, and this is the junction region, this one and this one. As the deflection width decreases, deflection width means this one is the defletion region, this one is defletion region at the junction, this one is deflection region. As the defletion region decreases, conduction region, because this one is conduction, drain and source, this will be increase, this width will increase, and drain current will increase. This is the first case, and in either way, when temperature increases, mobility decreases. as FET is negative, has negative temperature coefficient. So what will happen? Again ID decreases. So ID is affected by temperature in two ways. In first way this is increasing, in second way this is decreasing. That means ID is somewhat in the stability condition if temperature increases. That means if we increase temperature, ID, that is the current through the FET, will remain in a stability condition. So this will not affect or damage that device. So one thing to remember, that in case of temperature increment, VD, that means voltage drain source voltage will control the mobility, and gate to source voltage will control the depletion width. We have to consider these things. We have to remember this, which is controlling what thing. So next question is the type of power amplifier that exhibits crossover distortion in its output is. This is class B amplifier, and this is also called the push-pull amplifier, and this is the output, and this region is called the crossover. This is the crossover. This one is crossover distortion. Next question is, for resonant circuit with resonant frequency of 1 MHz, quality factor is equal to 50 and R is equal to 400. This is ohm. Find the value of C. So here nothing is given about as this is a series circuit or a parallel circuit. So you have to calculate in both the cases what is the answer and find out if the answer is exist in the options or not. So first thing we have to consider the series condition. In case of series, the quality factor is given as Q is equal to 1 by R root over of L by C, and quality factor is given to be 50. So 50 will be equal to 1 by 400 into root over of L by C. So we are getting that root over of L by C is equal to 20,000, and we can apply another formula, that is the F0, that is the resonant frequency. Resonant frequency is equal to 1 by 1 by 2 pi root over of LC. So what will be the thing? Here given that F0, that is the resonant frequency, is given to be 1 megahertz. So this will be, if we solve this one, we will get root over of LC, we will get 1.6 into 10 to the power minus 7. So we have to solve these two things to find out what is the value of C, because L is also not given. So if we find out this one, this is given and this is also given. So if we find out C square is this much and C is given to be 7.95 into 10 to the power minus 12, and this is 8, nearly equal to 8 picofarad, and 8 picofarad is not given in the option. Options are given 250 picofarad, 1000 picofarad, 1.25 picofarad and 500 picofarad. And here this is the series case, and if we consider the parallel case, because nothing is given, parallel case, if we consider the parallel case, in case of parallel, quality factor is given as R into root over C by L, and if we put the values, 50 is equal to 400 into root over of C by L, and we will find C by L to be 1 by 64, and root over of L by C we are getting from the previous one 1.6 into 10 to the power minus 7, and LC is equal to 2.56 into 10 to the power minus 14, and multiplying, if we multiply this one, LL will be cancelled out, and this will be C square will be 4 into 10 to the power minus 16, and this is 200 nanofarad. So nothing is given about this one. 200 nanofarad is also not given. So either option will be for series RLC circuit, this will be 8 picofarad, and for parallel circuit this will be 20 nanofarad, and nothing is given in the option. So next question is question number 113. an SMPS operating at 20 kilohertz to 100 kilohertz range uses as the main switching element. Which one is the main switching element of an SMPS, that is switching mode power supply operating at 20 kilohertz to 100 kilohertz? So what may be the device, switching device? Suppose first option is given thyristor, and generally thyristor is used below 1 kilohertz, below 1 kilohertz. So this is not the answer. Next one is Mosfet. Mosfet is used for below 100 kilohertz. So this is one thing preferable. Next one is triac. Triac is used for below 500 hertz, and this is given that 20 kilohertz to 100 kilohertz. So this is not preferable. Next one is UJT, unijunction transistor, and this cannot be used above, this can be used above 100 kilohertz. So but the range is given to be 20 kilohertz to 100 kilohertz. So here most preferable is Mosfet, and currently UJT is not used. Next question is slew rate is expressed in, this answer is volt per microsecond. Volt per microsecond. What is slew rate? Slew rate is defined as the maximum rate of output voltage change per unit time. That is maximum rate of output voltage change per unit time. That means voltage change per time. That means volt per microsecond, and it is denoted by the letter S. The slew rate helps us to identify the amplitude and maximum input frequency suitable to one operational amplifier, that is op-amp. So next question is the minimum number of NAND gates required to implement Boolean expression A plus A B bar plus A B bar C. So here this one is A B bar A B bar C. So this is A, if we take common A, then this will be 1 plus B bar plus B bar C, and this will be result A only. So as this is 1, this whole term will be 1, and as this is a single term, so no NAND gate is required. No NAND gate is required to represent the Boolean expression, because this one is single term, single variable A. So answer will be 0. Answer will be 0. This is a very good question. Next question is the slowest ADC among the following is analog to digital converter. What is the slowest analog to digital converter among these? Option A is flash type, option B is successive approximation type, option C is integrating type, option D is counting type. And this is also 2001 GATE electrical engineering question. So answer is the integrating type. Answer is integrating type, and this is the slowest. And if the question asked for the fastest is the flash type. So next question is most of the linear ICs are based on 2 transistor differential amplifier because of option A input voltage dependent linear transfer characteristic, option B is high voltage gain, option C is high input resistance, option D is high CMRR. So here answer is high CMRR. This is the circuit, differential circuit, 2 transistor differential circuit. Next question is question number 118. The output of logic gate is 1 when all its input are at logic 0. The gate is, all of the input are 0 and output we are getting 1. That means suppose this one is gate, we don't know what type of gate this is, and we are getting that here these input are 0, we are getting here 1. So for NAND gate, if all the inputs are 0, we are getting 1. This is the NAND gate. And in case of NOR gate also, if the inputs are 0 all, then we are getting also 1. And in case of JOR gate also, if we put input 0, we are not getting 1 here. So this is not the answer. First, JOR gate is not the answer. So here we will cancel out jar. Here AND gate is given, so this is not the option. And here XOR, this is not the answer, and this is not the answer. So here remaining is NOR and XNOR, because both NAND and NOR will satisfy this term. NAND and NOR. Another one is XOR or XNOR. So here is the XNOR. XNOR, we are getting 1 for each 0 value at the input. Next question is the path of the magnetic flux in a transformer has option A high reluctance, option B low resistance, option C high conductivity, option D low reluctance. So here what should be the core material for an ideal transformer? This should be highly permeable, that is low reluctance to allow the flux. Next is this have least hysteresis to avoid retentivity and coercivity. Next is no saturation magnetization to avoid harmonics creation, and next one is the high resistance to decrease eddy current loss. So here in the option given that high reluctance, this is not correct answer, because we need low reluctance to allow the flux to flow through it. So this answer will be low reluctance. And high conductivity is not also the option, because not also the answer, because this will cause higher eddy current loss. This will cause higher eddy current loss. And next one is high conductivity and low resistance, both are same. Next question number 20. A transformer operates option A always at unity power factor, option B has its own power factor, option C at a power factor below a particular value, option D at power factor depending upon the power factor of the load. So according to the load, the power factor changes in transformer, and this is the voltage regulation of transformer according to the load power factor. And this is a very important plot you have to remember. I have told many times this plot should be remembered for not only for the transformer but also for the transmission line voltage regulation and for also the synchronous generator or the alternator. This is the same voltage regulation curve we have to remember. That means for lagging load always the voltage regulation is positive, and for leading power factor load, the voltage regulation may be positive, may be zero, may be negative. This should be remembered. So what we are saying, that power factor may be anything depending upon the load power factor. Option D is the correct answer. Next one is advantage of synchronous motor over slip ring induction motor are that its option A power factor can be varied. This is not correct. This is one thing. This is correct, because power factor can be varied in case of synchronous motor widely from leading to lagging. And next is speed can be easily varied. Speed is never varied in synchronous motor, as this has constant speed. So this is not the answer. Next one is speed is independent of supply frequency. Speed is not independent of supply frequency. This is depending upon the supply frequency, that is 120 F by P, that is F is the supply frequency. This is the synchronous speed. And next option D is rotor has two slip rings, not an advantage. This is not an advantage. Having a slip ring is not an advantage. In case of slip ring induction motor there are 3 slip rings, and in case of synchronous motor there is 2 slip rings, and this is not an achievable advantages. advantage. So we will consider this one to be answer, because power factor can be varied in a wide manner. This is also an advantage, but in comparison to slip ring induction motor, this is an advantage, but not considerable. Next question is, a series generator is supplying power to DC bus bar. If the prime mover fails, then the machine will operate as option A, DC series motor rotating in the same direction, option B, DC series motor rotating in the opposite direction, DC series generator rotating in the same direction, and option B is machine will stop. So here what is given, series generator is supplying power to DC bus bar. If prime mover fails, suppose this one is given and prime mover is turning in this way, in this direction, and as this is a generator, current will flow in this direction, that means in outward direction. As this is a series DC generator, so IA and IF are in the same direction. But when the prime mover will fail, but this is already connected to the bus bar, and bus bar has infinite energy to give energy to this device. Now this device will get energy from the bus bar, and this will act as motor. And what will happen, both the field current and the armature current will be opposite from the previous condition. From the generator condition, in motor condition, both IF and IA will be changed. But if we want to change the direction of rotation of motor, we have to change either of a field, because torque is dependent upon phi Ia. So we have to either change this one or this one. If we change both phi and Ia direction, then this will be minus and minus, this will be positive. So as both IF, that is field current, and armature current is changing in the same direction, so the rotation will remain in the same direction as previous. That means as running in the generator, the rotation will be same, but it will be act as a motor. Rotation will not change, rotation direction will not change. So option A is the correct answer. That means DC series motor rotating in the same direction as generator. Next question is, a DC shunt motor having unsaturated magnetic circuit runs at 1000 rpm with rated voltage. If the applied voltage is reduced to half of rated voltage, the motor will run at, so here DC shunt motor is given and unsaturated magnetic circuit runs at 1000 rpm, and this is given that, and we know that EB, that is the back EMF is directly proportional to phi into N, that is the field flux into N is the rotating speed. So N will be proportional to EB by phi. So we can write that N2 by N1 is equal to EB2 by EB1 into phi 1 by phi 2, and this will be as this is given that when supplied voltage will be halved, we are considering that armature resistance to be 0, so EB will be equal to V. So what will happen, EB2 will be half of EB1, that means the supply voltage will be halved. So V2 is equal to V1 by V2, and IF is equal to V by RF, and IF will be IF1, IF2 will be, that is in second condition, the field current will be half of the initial condition, field current will also be halved, and that is why the flux produced by the second condition will be halved. So here EB2 by EB1, EB2 by EB1 is equal to EB1 is equal to half. So I have put here half, and phi 1 by phi 2, here phi 1 by phi 2 will be 2, phi 2 will be 2 here. So this is 2 and this is getting to be 1. That means N2 will be equal to N1. That means the speed will remain constant. Speed will remain constant. Next question is, for a stepper motor, which of the following torque has the highest numerical value? So answer is pull out torque. This is pull out torque. You must refer to what are the pull out torque, what is pull in torque, and what is detent torque. So I have also given here what are these things. You can take a screenshot of this one and read this one, or you can refer to any book or Wikipedia for this one. So next is, which of the following motor would suit applications where constant speed is absolutely essential? As this is given constant speed is absolutely essential, we will blindly consider the synchronous motor. We will blindly follow the synchronous motor because it has only the constant speed. So option C is the correct answer. So the next question is question number 126. The phase sequence of a three-phase alternator is RBY. If the direction of rotation of the field is reversed, then which of the following can be the phase sequence? So here the sequence is already RBY. That means RBY, and if the excitation direction changes, excitation field direction changes, so what will be the thing? The direction alternator three-phase sequence will be changed. And if we consider the option A, RBY, this is same as this one, because RBY, this is already same and this is not changed, and BYR, this sequence is same, BYR, the sequence is same, and the D1 is given YRB means here YRB, the sequence is still the same. So here option C is the correct answer, that is BRY, this is the direction BRY. Next question is, the coil span of an alternator is 160 degree. Which of the following harmonic component will be absent in the voltage? So here coil span is given to be, beta is given to be 160 degree, so alpha will be 180 minus 160, that is 20 degree, and alpha is equal to 180 by n. Alpha is equal to 180 by n. N is the harmonic level, and so as here 20 is equal to alpha, 20 is equal to 180 by n, and n will be ninth harmonic. So here to reduce ninth harmonic, we have to wind the winding like this, such as the coil span will be 160 degrees. So here answer will be ninth harmonic. Next question is question number 28. The distribution factor of a uniformly distributed three-phase alternator is. So for three-phase alternator, the KDU, that is the distribution factor for uniformly distributed winding. This is sin m gamma by 2 by m gamma by 2 into pi by 180. This is the formula. And what is m? M is the slots per pole per phase. Slots per pole per phase. And what is the gamma? Gamma is the slot angle. And m gamma is the angle subtended by a phase. Angle subtended by a phase. So here three phase is given. So what will be the angle? angle will be 180 by 3. 180 by 3, number of phase is 3. So here 180 by 3, and this is for narrow phase spread, and so this will be KDU will be sine 60 by 2. 60 is 180 by 3, sine 60 by 2, m gamma is 60, so sine 60 by 2 by whole by 60 by 2 into pi by 180. So this, if we solve this one, this will be 3 by pi. This will be 3 by pi. Answer will be 3 by pi. Answer will be 3 by pi. Suppose the question is given like, suppose the question is given for the single phase alternator. So for single phase, this will be 180 by n. M gamma will be 180 by n. N is now 1. Phase is, number of phase is 1. So this will be, m gamma will be 180, and this will be sine gamma m gamma by 2, that means 90 degree, by m gamma by 2, that means again 90 degree, into pi by 180. Sine 90 is equal to 1, and this is cancelled out to be 2, and this will be 2 by pi. This is two important questions. Now next question is, the voltage regulation of 0.95 lead power factor is 0 for an alternator. If so, the voltage regulation for 0.9 lead power factor with all other conditions remaining same. I have already told that you have to remember this plot, at least this plot for voltage regulation. So what is given? Given that voltage regulation for 0.95 lead power factor is 0. 0.95 lead power factor. Here this one is lead power factor, and this is for 0.95. This is voltage regulation is 0. And so if so, the voltage regulation for 0.9 lead power factor for 0.9, that means from this, because if we go this way, this will be unit power factor, that means 0. Greater than 0.95. So 0.9 lead is less than 0.95, that means in this direction, and if we go in this direction, voltage regulation is coming to be negative. So answer will be B. Next question is, a single phase 2000 volt alternator has armature resistance and reactance of 0.8 ohm and 4.94 ohm respectively. The voltage regulation of the alternator at 100 ampere 0.8 leading power factor is. So here what is given? V is given, R is given, X is given, I is given, cos phi is given, and we have to find out sin phi. This is cos phi is given, phi is 0.8 and sin phi will be 0.6. And what is E? That is the excitation voltage. Excitation voltage formula is this one, and here negative for leading power factor, and positive, here positive is for lagging power factor, and in this case this is given to be leading power factor. So if we apply the formula, we are getting E to be 1822.32 volt, and voltage regulation is E minus V by V, that is 1822.32 minus 2000 by 2000, which is equal to minus 8.9%, minus 8.9%, that is option B. Next question is, which of the following generators is used for DC arc welding application? This is differential compound generator. Next question is, the power input to the rotor of a 400 volt 50 Hz 6 pole 3 phase induction motor is 20 kilowatt. The slip is 3%. The frequency of the rotor current is. So here the input frequency is 50 Hz. So we know that frequency of rotor by frequency of stator is equal to the slip. So frequency of rotor, that is F2, will be slip into frequency of stator, and frequency of stator is the supply frequency, that is 50 Hz, and slip is given to be 3%, that means 3 by 100 into 50, and this is coming to be 1.5 Hz. So answer will be 1.5 Hz, option B. Next question is, what does the shunt resistance component in the equivalent circuit of an induction motor represent? So here this one is the basic equivalent circuit which is analogous to equivalent circuit of a transformer, and this is the equivalent circuit of an induction motor. And here question is asking regarding this resistance, for which this resistance is representing, what this resistance is representing. So now here if we see this one, here IE, this one is IE, and IE current is called the exciting current, and IC is branch of IE. IE is equal to IC plus IM, and IC is the core loss component and IM is the magnetizing component. So IC is only for the core loss, not, you may think that core loss plus windage and friction loss, but this is not the true answer. Here is core loss. Windage and friction loss may be included with this one, this resistor, but not with this one. In case of because V1 IC, that means voltage across is V1 is the voltage across this one, and V1 IC is the power consumption due to RC only, and this one is the no load loss minus friction and windage loss minus negligible starter and rotor I square R loss, that is the copper loss, and no load loss from the no load test we can find out the mechanical loss also, like this. I am not explaining this one right now. So answer here is the core loss. Next one is, in ceiling fan the angle between auxiliary winding and the main winding is, this is 90 degree, because single phase induction motor is nothing but a single this is ceiling fan is a single phase induction motor. So we need a rotating magnetic field to run any induction motor. As we have a single phase, we have to split this phase to two angles. That means in physically two angles. This can be 90 degree. To maintain to form a rotating magnetic field. So this is 90 degree. Next question is question number 35. At dead short circuit at the terminal of an alternator, the current I is at, this is 0 power factor lagging. So when short circuited, the impedance in the circuit is the synchronous impedance, and this is, in case of alternator, this synchronous impedance is more inductive, predominantly inductive. So as this one is inductive, this is ZPF lagging. Next one is, when alternator excitation increases and machine is operating at lagging power factor, then option A, armature current will increase, armature current will decrease, armature current remains unchanged, armature voltage remains unchanged. So our convention is for alternator is a generator, and as it is a source, if it gives or delivers power, then this is positive and this is lagging, and for reactive power deliver, and negative for absorption. This is our convention for source and load, and as this is a source, this is our convention. And what is the Q? That is the reactive power, V by Xs into E cos delta minus V. And so for E cos delta, that means excitation is higher. If we increase excitation, this will be E cos delta will increase, will be greater than V, and this will be positive. Q will be positive, and that means it will deliver reactive power, and this will be lagging load. And under excitation means when E cos delta will be smaller than V and Q will be negative, this will absorb reactive power, and this is the leading condition. Here given that already this is operating in lagging condition. In this question given that already this is operating in lagging condition. So when excitation increases, it will be more lagging and more magnetization current it will deliver. That means higher armature current it will draw. Higher armature current it will draw or generate. Higher armature current. So this is the V curve and inverted V curve. So V curve is generally drawn between the field current and IA, that is armature current, and in case of inverted V curve is drawn between the IA field current and the power factor. This thing we have to remember. And as this is given that in this question this is given that alternator excitation increases and the machine operating at lagging power factor. Excitation increases and machine is lagging power factor. That means this one lagging power factor, this one is lagging power factor, and excitation, as excitation increases this current increases. From this it is clear that IA increases, armature current increases. Next question is question number 137. In an amplitude modulated wave, the value of V max is 10 volt and V min is 5 volt. Then percentage modulation is, and percentage modulation or modulating factor is given like M is equal to V max minus V min by V max plus V min, and this will be 10 minus 5 by 10 plus 5, and this is 33.3%. Next question is VSWR of a transmission line is always, and first thing, what is VSWR? VSWR is a voltage standing wave ratio, and this is defined as the ratio of maximum voltage to the minimum voltage in standing wave pattern along the length of a transmission line structure. Standing waves represent the power that is not accepted by the load and reflected back along the transmission line or the feeder, and it varies from 1 to infinite. This is the VSWR, and VSWR transmission line is always greater than 1, So here I have written something. So this one is VSWR. I have mistaken. VSWR is equal to 1 plus zeta, and here zeta is the reflection coefficient. Here is the zeta is the reflection coefficient, and here as this is a mod, this is always a positive value. This whole is a positive value and this whole is a positive value, and that is why 1 plus zeta by 1 minus zeta will always be greater than 1. Next question is communication between satellite and ground station is always through line of sight propagation, and the common example is the dish antenna or any D2H antenna on your roof is operating on the line of sight operation, and this is directly communicating with the satellite. Next is a mast antenna is used mainly for option A UHF ultra high frequency, option B short wave, option C medium wave, and option D very high frequency. So this is medium to high frequency. What is mast antenna? Mast antenna is generally the tower structures. Generally the tower structures, mobile towers and other structures are mast antennas. Next one is a standard AM broadcast station is allowed to transmit modulating frequencies up to 5 kHz. Up to 5 kHz. If AM modulation is transmitting on a frequency of 980 kHz, compute the maximum minimum upper and lower side bands and the total bandwidth occupied the AM station. And here in the option only bandwidth is given, and here only bandwidth is given, and what is the frequency? 980 kHz, and we have to find out upper and lower, and this one is upper 985 plus 5 and minus 5. So what will be the bandwidth? Bandwidth will be 10. 5 plus 5 or 2 into 5 from 975 to 985. So this will be bandwidth will be 10 kilohertz. Next one is AM transmitter has a carrier power of 30 watt. The percentage of modulation is 85%. Calculate the total power. So here different type of AM is present. So here if we consider the basic, and this one is the standard type, this is DSB-FC type, and for this one the formula is PC into 1 plus m square by 2, and this is PC is given to be 30 into 1 plus 0.85 square by 2. And what is PC? PC is the carrier power frequency, carrier power is 30, and this is coming to be 40.83 watt. So option B is the correct answer. As nothing is given, I have selected this one, and other types are, here I have selected DSB-FC type, and other types are suppose SSB-SC type, another one is SSB-SC, and for this one formula is PC into m square by 4, and the answer will be 5.4 watt. If this is given, answer will be this one. And another type is DSB-SC type. This one is DSB-FC, and this one is SC, and here this one is also PC into m square by 4. This one is PC by m square by 2. This was not 4, this one is 2, and here answer will be 10. Answer will be 10 watt. So as nothing is given, I have chosen the standard one. Standard one is this one. The next question is, if peak transmitted power in a radar system is increased by a factor of 16, the maximum range will increased by a factor of, this answer will be 2. And how? This one is range is directly proportional to p to the power 1 by 4. This is the condition. If diameter is given, as here given is 16, increased by a factor of 16, this will be, range will be directly proportional to p to the power 1 by 4. That means 16 and its fourth root is 2. So range will be increased by factor of 2. Suppose this is given in terms of diameter, so what will be the relation? Range is directly proportional to diameter. Suppose diameter is increased by a factor of 16, then the range is also going to be increased in the factor of 16. So next question number 144. A high PRF. What is PRF? PRF is the pulse repetitive frequency. Implies which of the following statement is not correct? Option A, makes return echoes easier to distinguish from noise. Option B, makes target tracking easier with conical scanning. Option C increases the maximum range. Option D has no effect on range resolution. Here option C is not correct. All option B, C and D are correct. Next is, if IFBW of a radar, IF bandwidth, this is bandwidth of a radar receiver is inversely proportional to, this is pulse width, bandwidth is inversely proportional to the pulse width for a radar receiver. Next question is, interlacing is used in television to avoid flicker. This is direct question from communication, and this is to avoid flicker. Next question is, a return echo received after the allocated pulse interval, then option A, it will interfere with the operation of the transmitter. Option B, receiver may be overloaded. Option C, it will not be received. Option D, the target will appear closer than it relay is. So here option D is the correct. Return echo arrives after the allocated pulse. That means the target will appear closer than that relay is. So this will be closer than relay. So next question is, amount of solar radiation received on a unit area exposed perpendicular to sunlight is termed as. So this is the solar insolation, not insulation. Solar insulation is nothing. And solar radiance I have given here. What is solar constant? First thing, solar constant, there is a term solar constant, and solar constant is given as is the average radiation intensity falling on an imaginary surface perpendicular to the sun's ray and at edge of Earth's atmosphere. This is the imaginary surface, and this is called the solar constant. Average radiation intensity falling on a, this is average radiation intensity. And what is solar radiation intensity falling on the surface is called irradiance. There is no radiance, so this should be irradiance. Irradiance is a term, solar irradiance is a term exist, but here this will be solar insolation. What is solar insolation? Solar insolation is this one. Solar insolation is same as solar irradiation, and this is measured by watt per meter square, and this is the energy falling per area as given on a unit area, radiation on a unit area. So this is solar irradiation or irradiance or insolation, not insulation. Here option D is the correct answer. You may think that from which these questions are coming. So this is 2012-13 question, and you don't know about the syllabus, and at that time this is the paper 2 and paper 1 is also from the general part. So at that time the syllabus is very vast and we don't know about that syllabus. So these questions are from communication and solar, etc. So this may not come now in this year, this type of question, because already they have mentioned the syllabus, perfect syllabus for electrical part. Next question is, an IGBT has 3 terminals called collector, emitter, gate, and we know that IGBT is the combination of BJT and Mosfet. So the combination also, the terminals are also the combinations. From BJT we have collected collector and emitter, and from Mosfet we have collected gate and combined it together. So here the terminals are collector, emitter and gate, Question number 150, and this one is the last question. A 4-pole synchronous generator driven at 1500 rpm feeds a 6-pole induction motor which is loaded to run at a slip of 5%. What is the motor speed? What is the motor speed? So for synchronous generator, given that synchronous generator speed is given, and we have to find out the frequency. 120 f by p. F is equal to ns, that is the synchronous speed, into p, number of poles, by 120. So we are getting 50 hertz frequency. 50 is the output frequency of synchronous generator which feeding to the induction motor. So as induction motor is supplied with 50 hertz frequency, so what will be the ns, that is the synchronous speed? Synchronous speed will be 120 f into 6 poles. Induction motor has 6 poles, so this will be 1000 rpm, and as slip is 5%, so rotating speed will be 95 into 1000 by 100, so this will be 950 rpm. So here answer will be option C, 950 rpm. So this is the end of this topic, and thank you for watching up to here.